So we're here with Dr. Pollock, um, famous for what is called one of the most important scientific discoveries of the century, known for structured water and his studies on structured water and a number of other things. Uh, Good morning, Dr. Pollock. How are you doing?
I'm doing fine, Ben. Thank you for having me. Delighted to be here.
Yes, we have a lot of fans, of your work, constantly commenting on it and asking if I could um, talk more about it. And in fact, after our previous interview, your name was one of the few that was brought up many, many times in terms of who do you need to get on here next.
Oh my goodness, I'm flattered. Thank you.
Absolutely, absolutely. Okay, so some of the topics that I have in mind, and I think a good way to sort of bridge into this is I was reading the article where it described your discovery of the fourth phase of water as one of the most revolutionary or most important discoveries of the century, and one paragraph really stood out to me among all the other ones, and it was the beakers experiment where we ran the current through the beakers that were full and touching, and you slowly move the beakers apart, and a bridge of water was formed between them and maintained between them. Could you talk a little bit about that, because that is fascinating?
Sure. Well, the person who's responsible for most of the work on that is Elmar Fuchs, originally from Austria, now works in Holland. We've tried the experiment in our lab, and we get essentially the same results that he got. But it's really cool because you put water in the two beakers, and you put two electrodes, one in each beaker, and you impose a high voltage, and then you get a little bridge that runs, a bridge of water that runs from basically from one beaker to the other beaker. And the interesting part is that if you pull one beaker away from the other beaker after this has begun, the bridge doesn't collapse. It sustains itself, and it sustains itself for a distance of 3 or 4 centimeters, and it sustains itself indefinitely. This is amazing because you don't expect water to behave this way. There's that bridge that forms. It's a bridge of water, and it forms between the two beakers, and sometimes it's so straight, which means stiff, that it looks as though you could actually walk across it. Obviously, you can't. So this is one of the really interesting observations because it implies that something is missing from our understanding of water, because nobody could ever imagine a bridge spanning more than an inch between beakers. And I think the explanation for this lies in this fourth phase of water that we found. It's a kind of crystalline water, and crystals, as you know, can be pretty stiff, and I think in this case the crystals are very stiff, and really what this is a bridge of fourth phase water rather than a bridge of ordinary H2O. I think that's the likely explanation. It's really dramatic to see.
Absolutely. Now, this fourth phase of water would fall in between the solid ice and what we consider to be the liquid H2O phases, correct?
Exactly. Right. It's the structure of this, from the evidence that we've seen. The structure is not so different from ice. It's not ice because ice is solid, and this fourth phase, or sometimes we call it EZ water. It's short for exclusion zone.
Absolutely.
The reason for exclusion zone is because this crystalline phase of water excludes practically anything that wants to get into it. So exclusion zone, easy, fourth phase, whatever you like. And this is this phase exists wherever you find a hydrophilic surface, that is a water-loving surface. By water-loving, I mean, if you were to lay the surface horizontally and drop a droplet of water, instead of beating up like Teflon, like hydrophobic surfaces, the water spreads out, and that's hydrophilic surface. We found that next to essentially all hydrophilic surfaces, this fourth phase crystalline water builds. And you're right about it's kind of ice-like, and we found that if you freeze water, you don't go from water to ice. You go from water to the fourth phase and then to ice. And if you melt the ice, you go from ice to fourth phase, then to ordinary water. And this actually explains quite a lot. It explains why sometimes, for example, when you see ice melt, the water is not the kind of usual, almost black water that you see in the sea, or dark blue, or it's really hard to define the color. Often it's a kind of turquoise color, and I've seen this in the Cascade Mountains nearby, both in Canada and in the U.S., and I've seen it in Austria, in Innsbruck, just looking over from that lovely bridge, and you can see the sort of blue-green water. And everybody thinks it's the minerals that give it the color, but it's interesting that the color is the same no matter where you are, but the minerals are probably different, you see, but you get the same color. And I think the color is formed because as the ice melts, it's full of easy water, and that easy water surrounds the different materials and or the different minerals that are there, and as a result, you're really seeing easy water. We found that this water fluoresces, and so you get light that's coming from the environment, and then you get a fluorescent light that comes out. It's would be a kind of bluish green, sometimes a little violet in it. And I think that's the reason why you see this color. So yeah, this fourth phase is in between ice and water.
Well, that's amazing. There's something I was actually going to ask you about the exclusion zone a bit later, but since you brought it up, and since you mentioned that these hydrophilic surfaces tend to have the liquid crystalline water or the easy water build up near it, it's invoking a memory I have about a recent article about how little we understood about static electricity. And the discussion was that they studied particles rubbing up against one another, and they found that they didn't have the surface charge or the charge in the molecules colliding to create the static electricity. And one of the things that they thought was a good avenue for exploration was they noticed that all these things happened to be coated in a thin layer of water, and that it could have been, that could have held the genesis of that electricity. But something interesting, I want to read a sentence to you that I'm pretty sure you're going to be familiar with, and I quote, "We target areas in which understanding seems too complex to be valid and penetrate, or at least we try to penetrate, towards the core of the truth." And this is from one of your sites describing what you do in your laboratory, and I think it kind of drills down to, the question I want to ask next, which is, how did you even think to begin investigating something like this? What gave you the spark to look into the core of truth of water?
Frankly, my whole career has been based on finding truth. In science today, most practitioners of science are following the mainstream, which is certainly worthwhile. But in my opinion, the ultimate value is to look into phenomena that are not well understood or not particularly known, because that's where the gains are to be made. And so we follow a course that's a bit different from the mainstream. We look into areas that are really undefined, not well researched, not well studied, and we go into that. I started my career and spent many years doing that in the field of muscle contraction. How do the proteins organize themselves to produce the force and the motion that we observe? And there's a theory that's out there, and the people responsible for the theory are people with very big names. For example, the late Sir Andrew Huxley, who passed recently. And he was an extremely important Nobel laureate, former master of Trinity College, Cambridge, knighted by the Queen, president of the Royal Society, whatever. His theory. So there are many people who follow his theory, and such a great and distinguished person can hardly be wrong, we think. However, we found that his theory didn't fit so many observations, and frankly, the theory is, if you look at all the observations that don't fit, the theory is essentially inadequate. It's wrong. It doesn't fit. It's not really even close, yet it fills the textbooks. And so we did many experiments to look into what actually happens, and of course we came up with a different point of view. But what struck me during my years doing that is, if you look at the accepted mechanism of how the proteins interact with one another to produce the force, there are many proteins and many theories based on the proteins, but all the diagrams, all the pictures, everything you see in the textbook is missing the most important ingredient, water. And if you look at these pictures, it looks as though these proteins act in a vacuum. There's no water, but obviously there is water. Our muscles, by volume, are roughly 2/3 water. And, since the water molecule is so small, in order to fill up the 2/3 volume, you need a lot of water molecules. And if you do the arithmetic, it comes out that of all the molecules in muscle, the same for other tissues, of all the molecules that form muscle, 99% of them are water molecules. And it struck me as weird that 99% of all the molecules in our muscles don't do anything. They're simply there to bathe the more important molecules of life. How could this be? Now, people knew long ago that water was central to everything in biology. The most maybe recognized person to do that is Albert St. Georgi, who was a Nobel laureate. He discovered vitamin C, but he spent most of his time studying muscles. And I found it striking that his idea of how muscles contract, and I finally, it was only a couple of years ago that I came across his book on the subject, and in the book he describes how muscle contracts, and the trigger is a destructuring of the water inside the muscle. And oddly, 50 years later, it took a long time, we came to exactly the same conclusion. So his work has been forgotten. And he knew that water was central to everything in biology, and one of his most famous quotes is, life is water dancing to the tune of macromolecules. So he knew that water was absolutely in the center of everything biological, a view that's been completely forgotten. So we picked up from that point, and the book that I wrote, not the recent one, the book I wrote in 2001, it's called Cells, Gels, and the Engines of Life. I tried to bring forth St. George's and other people, including Gilbert Ling, another famous scientist who also had mounds of evidence showing that water was so important for all biological activities, and that the water inside the cell was organized, crystalline, structured, not ordinary H2O that you find in a glass. So the book attempted to bring forth some of those concepts and apply them to modern biology. And the conclusion that I drew in that book, which is actually quite popular, it's gained increased popularity even over the past 2 or 3 years, new reviews 12 years after publication. The central idea was that in virtually every function, every principal function in cell biology, from muscle contraction to cell division to transmission of information in nerves, all of the above and many more, that if you really wanted to understand how these things worked, water, you need to understand the behavior of water, because water is central to all of these. And so we started studying, after the book came out, we started studying water experimentally, and what we found blew our mind. I just can't, that's in the most recent book, which is called The Fourth Phase of Water. And there we explore the properties of this kind of ordered water. most of us don't think that water has any order. Ordinary H2O is simply a bunch of water molecules bouncing around, hitting each other at different angles, and making connections or transient connections with one another. But we found that this fourth phase of water, which by the way had been predicted 100 years ago by famous physical chemists who said there's no way that you can understand the behavior of phenomena involving water unless there's some kind of fourth phase. And what we've done in this latest book that described, and also of course many publications, scientific publications, is to identify and explore the role of this fourth phase. It's it's almost everywhere, wherever water, wherever there is some surface in water. That surface can be, as I mentioned, an ordinary hydrophilic surface immersed in the water, like sometimes the glass itself can do this. Or if you have molecules in the water, dissolved in the water, or particles suspended in the water, all of these nucleate this buildup of this fourth phase of water. So it's everywhere, and one of the interesting features is it's kind of like a battery. So if you can imagine some large, extensive surface sitting next to water, most of us think, well, nothing happens. It's just water next to a surface. In fact, there's a major change that occurs next to the surface. The H2O molecules undergo a chemical transformation into something different, and that's the fourth phase. And it's not just one or two molecular layers. This change builds, and it builds out to up to millions of molecular layers. It's a really gross change of structure. And there are two features of this that I think are central and interesting and unexpected. The first, it's not neutral. H2O is neutral. This fourth phase is actually negatively charged, and the region of water that's beyond the fourth phase is positively charged. So it's kind of like a battery, and this comes about because the phase builds from ordinary water, H2O, and H2O can be broken into negative and positive components. And so, in general, the negative component builds this fourth phase, easy water, a kind of distinct structure that exists next to the hydrophilic surface. And the corresponding positive charge is left in the water. So you have minus and plus. It means you have a battery. Now, we found that you can extract electrical energy from this battery. So that's one point. Second point is that the energy for separating the charge, for building this battery, comes from light. And this was another surprise for us. Every battery needs to be charged. You have a cell phone, and it runs down, and you plug it into the receptacle. But there's no receptacle here to plug into, and so the question arose early on, well, where does the energy come from? We couldn't figure it out. And one day, a student grabbed a lamp, and he was walking by the bench where we had the chamber set up where we could see this phase of water, and he shined the light on the chamber, and we looked in the microscope, and we saw that the exclusion zone grew like crazy. And then when he took the lamp away, it retracted back to its original shape. So, it didn't take a genius to figure out that, it looks like light has some effect on this, that photons might constitute the energy for buildup. And indeed, so we did many subsequent studies, and we found that light, not only visible light, but ultraviolet light, infrared light especially, was very important for building, not only building this phase of water, but separating the charge. You might say charging the battery. And this has a lot of implications because, first of all, infrared energy is free. Now, why do I say free? Well, it's everywhere in the environment. So I'm sitting in an office, if I block out the window, which will happen soon because of some construction, and turn off all the lights, and it's completely black, and I whip out camera, I get a beautiful image of everything inside the room. And it's an infrared camera. It detects only infrared energy. It's like a night light, a night camera. And even without visible light, you get beautiful image, and therefore that means that everything is radiating infrared light. We can't see it with our eyes, but it's there, and the camera can pick it up. It's free. It comes free. We learned when we studied chemistry about free energy, and that concept for some was a little bit complicated. This is not complicated. We can tap the energy freely from the environment, and this energy is what builds the fourth phase of water and separates charge. So it's a very nice system in which the fourth phase builds automatically from the energy that's freely available. Sorry, long answer to a short
No,
question.
that makes a lot of sense. The first part it would explain why you can find the structured water in the water that comes from plants, especially because they are wholly dependent on that light. As you were saying that, I was wondering in my head how the water deep underground becomes structured, if it's hidden from the light.
Yeah, it's a good question. So the first point, remember, is that it's not the visible light that is. We use the term light in a kind of loose sense. Light is, by physicists, means any kind of electromagnetic radiation, and that includes the small segment of the spectrum that we call visible light. It also includes infrared, it also includes ultraviolet, and it includes many other wavelengths throughout the spectrum. So I apologize for this, you might say, technical use of the word light. It's the infrared and some aspects of ultraviolet that are responsible. And when you're underground, there's still plenty of infrared light that comes out, plenty that's available to power this. So that's not really an issue. But underground, you have a few phenomena that are occurring. First of all, there's pressure. Okay, so there's the weight of everything above these underground sources or aquifers, if you will. That's the first point. And pressure, we found experimentally, if you take water and you put pressure on it, it creates fourth phase water. Why is that so? It's so because the fourth phase water is more dense than ordinary water. It takes up less space. So if you put pressure on some substance, that substance always wants to adopt the most dense kind of structure. And so there's a shift in structure from ordinary water to easy water. So the pressure on the water below helps to create easy water. And the second is that water is full of minerals. As I mentioned, around every mineral, easy water builds, because these minerals have surfaces, and the surfaces are what we need to build the easy water. So it means that when you take water from beneath the ground, and many of these springs are claimed to have health benefits, and I think it's possible that they do, because of the pressure and because of the salts and other minerals, there's a lot of easy water. And if you drink easy water, what you're doing basically is replacing the easy water in your cells that may be somewhat deficient, you may be slightly dehydrated, and so that's good for your health. And the same with plants. You mentioned that plants contain easy water. Well, sure, because plants are built of cells, just like we're built of cells. And if we have easy water in our cells, and the evidence suggests that that's the water that the vast majority of water in our cells is easy water, is not H2O, you see. And it's the same with the plant cells. So it's great to eat raw plants, or many of them, because you're essentially replacing the easy water in your cells with easy water from the plant cells. It's really as simple as that. And some people do juicing. We just did that this morning. My wife likes to keep the family healthy, and so we have some plants, green plants, and she takes some of those, and some organic plants that we purchase and puts them through the juicer, and out of that comes a kind of juice extract. And many people are using that, and studies have shown real health benefits from it. And I think the health benefits occur mainly because you're drinking easy water and replacing the water inside your cells. So yeah, that's the reason why plants, raw plants, are good for your health, and that's the reason why the water under the ground, being full of the same water that's in the plant cells, in our cells as well, why it should be good for you, good for your health.
Well, that's terrific. And you also, I think I'm going to head and extrapolate that cooking, and especially probably microwaving the food, might do something to unstructure the water. Um,
It might. I can't say for sure. I haven't studied it, but one of the students has been measuring the electrical potential of various foods. Now that sounds weird, but if you think about it, since a plant or us or whatever consists mostly of cells, and it's known that the cells are negatively charged, that's been established for 60 years or so. There's no controversy about it. Basically, we're negatively charged and the plants are negatively charged, and so we're not neutral. And we've actually made measurements of that, and so anything we can do to boost our negativity, so to speak. I hate to use that word because I'm quite a positive person, but I mean, electrically is the point, that we can benefit from that, and so the plants essentially give us negative charge because the water inside the plant is negatively charged, so we can get that. We can also get it from connecting ourselves to the earth. The earth is negatively charged, and people who have studied this concept of connecting to the earth, so-called earthing or grounding, they've shown real health benefits. And I think the health benefits are simply because the negative charge from the earth is electrically, we connect ourselves electrically, and so we get, you might say, recharged. And this negativity that fills our body and fills our cells is essential for life. Cells that are very highly negative, as studies have shown, are healthy. And when the cells lose their negativity, they're less healthy. And the reason for this negativity, by the way, I believe, is simply because the cell contains negatively charged water. And therefore, it's a kind of no-brainer that if you stick an electrode in the cell, you get negative charge. On the other hand, there's a prevailing theory that the negativity inside the cell is due to some membrane pumps and channels. And I've challenged that point of view in both of these books. I think it's erroneous, and other people are coming to that point as well. The reason the cell is negatively charged is largely because it's full of negatively charged easy water. As simple as that. We get dehydrated so easily, particularly when your hair starts turning gray. Kids or embryos are something like 90% water, and as we grow older, we continually lose water. And somebody whose hair is turning gray is perhaps 60% water. In kids, maybe 75% water. So we keep losing water, which means basically we're chronically dehydrated. A lot of studies have shown that hydration is very critical for health. So we need to rehydrate. And by rehydration, it means we need to supply easy water to our cells. The easy water is surrounding every protein inside your cell. And the function inside the cell is mediated by proteins. The proteins will fold or change configuration from one to another configuration, and that's the work of the protein. That's what makes the cell do its job. And however, these proteins are surrounded by easy water. If you don't have enough easy water, if you're dehydrated, then your proteins can't function as well, and you got a pathology. Sometimes these pathologies can be reversed by fairly simple means. I've seen evidence that drinking certain kinds of waters, although this seems to verge on impossibility, but I've seen hospital records showing how drinking consistently the right kind of water can have a really positive effect on health. So I'm not sure where this question started, but it ended up with water and health.
Well, I'm very glad it did. I'm very glad it did. I will. There's been a lot of discussion, especially on our website forums, about how to get structured water. There are a lot of people that watch that are very familiar with the websites, and there was some very lively discussion about spring water and whether or not that's got structured water, whether or not it becomes unstructured at some point when they're taking it out, or when it's bottled, or when it's sitting on your shelf. But yeah, I definitely, I'm glad you touched on the health aspect. Let's say somebody wanted to look more into your current research. How would they go find it? And also remind us of the name of that new book of yours.
Yeah, the new book is called The Fourth Phase of Water, Beyond Solid, Liquid, and Vapor. And you could just look under The Fourth Phase of Water. There are several places you can get it. The publisher's website is ebnerandsons.com, ebnerandsons.com. You could also get it at the usual sources. And so it's gotten some good reviews. I think it's become really popular. And sorry, there was another part of your question.
Well, you know, that's pretty much you know, how they would go and find your latest stuff, and I will of course have tons of links to relevant websites, including the Pollack Laboratory. But there is one last question or topic I wanted you to touch on, and it diverges perhaps a bit from what we've been talking about. I want to talk about IVS and your involvement with the Institute for Venture Science, your thoughts on why it's important to have this branch of, I don't know if you want to, you know, pigeonhole it as mainstream challenging science and scientists, but it is in that vein. And just a quick little talk about that. You already mentioned you know, the problems with just towing the mainstream line a bit earlier. But yeah, IVS, because I know that's been another topic that people want to hear about.
IVS is short for the Institute for Venture Science. So it's kind of like, you know, like venture capitalists, although we're not that. Venture capitalists may invest in a dozen different businesses thinking that maybe one will turn out to be a gold mine, and that's kind of runs parallel to what we're trying to do. Let me back up and say that science is in trouble right now. If you ask yourself, ask yourself to identify a breakthrough in science, a breakthrough in fundamental principles of science. Now, we can all name technological breakthroughs. They occur all the time, and these breakthroughs come because various companies are invested in helping to produce these breakthroughs because they can earn something from it. But if you ask yourself how many fundamental scientific breakthroughs, or maybe put it a different way, ask yourself, can I name in any field of science a fundamental breakthrough that's appeared in the last, say, 30 years or even 40 years, in any field of science, something that has really changed our world? I've asked this question to scientists and non-scientists, and they stumble immediately. It's really hard to think. If it was 100 years ago, it'd be easy, right? Because you'd start thinking about Einstein and relativity and Max Planck and Curie and all these people. Breakthroughs, fundamental scientific breakthroughs were occurring, I wouldn't say annually, but on a regular basis, and everybody knows about them. It's really hard to identify anything similar that's occurred in the past few decades, despite huge amounts of funding. Okay, there was not much funding 100 years ago. Right now, there are many billions that go into funding science, and we hear a lot of hype in newspapers and magazines about all the promises, you know, for curing cancer, and etc. But rarely do these promises actually materialize. I know one breakthrough, that's, I think, real breakthrough, occurred about 20 or 30 years ago. Barry Marshall, and he was looking at ulcers, and he came to the conclusion that ulcers were caused by bacteria. And at that time, that was so radical because everybody knew that ulcers were caused by worrying, and he could convince nobody. And so he finally swallowed the bacteria himself, and he cured himself with an antibiotic. And then they gave him a Nobel Prize. So that is, I think, a conceptual breakthrough of some magnitude. And by the way, Barry Marshall is on our advisory panel. So what is this institute? It's to restore the concept that breakthroughs are possible. Okay, and the way it works is this: we're looking for proposals coming from you, anybody, proposals that often, you might say, challenge promising ideas that challenge conventional or mainstream views. There are many of them out there, and I know of many in many fields. Most of us don't know about them because the major figures in the field, it's not to their benefit to advertise that there's somebody out there who's challenging the view that made them famous, you see. So it seems it's not in their best interest to do that. And so the promising ideas are often suppressed. So we're going to make it possible for people who present ideas, and obviously we don't want the flaky ideas, and we're going to vet them in a very effective way that we've figured out. And the really good ones, the promising ones, we're going to support abundantly with funding. But see, there's one more aspect. Even if a scientist receives ample support from a funding agency, still the idea will not go mainstream, or it's unlikely to go mainstream. The reason is that people have egos. They cling to the ideas that they've espoused and supported, and if there's a challenge to those ideas, they often feel uncomfortable. And I've seen this many times. People who have opposing ideas are ridiculed. They're considered nutcakes, crazy, denialists, what have you, and they can't gain any traction. However, you can solve this idea, and our plan is an integral part of the plan is if you propose to us, let's say, a round Earth idea. Everybody knows the Earth is flat, but you propose that it's round, and you come to us with reasonable evidence and ideas, and we hear from the flat Earth people, and they really can't defend against your idea, and it looks like this is an important topic, and that you look like you have good arguments, and we fund you. Of course, even with funding, you're not going to make too many inroads, because the more evidence you collect, the more resistance you'll get from the mainstream people. However, what we plan to do is to fund not only you, but we're going to look for other laboratories, up to even a dozen of them around the world, who share your vision that the Earth might be round. See, and then next year at the annual meeting of the Shape of the Earth Society, instead of one person reporting round Earth, you have 10 or 12 laboratories who are independent of you, reporting using different methodologies, different instruments and such, that, hey, they also are finding that the world is round. It's impossible to ignore a dozen laboratories who are reporting the same finding. The young people will immediately be awakened to these new and interesting findings, and despite the resistance of their mentors, there should be a revolution quickly. And quickly meaning a few years, perhaps 5 years. And we're going to be funding not only the idea that the Earth is round, but dozens of other kinds of questions and hypotheses throughout all of science. And the expectation is that we're going to see many revolutions. The dearth of revolutions that we've experienced over the past 3 or 4 decades, something will happen, and science will be revitalized. And, We need this kind of revitalization. It's not only the intellectual achievement of understanding the world around us, but also we have a lot of problems. Water is running short, energy is running short, climate issues. People are getting sicker and sicker with chronic issues. These need solution, and they've been resistant to solution. In the past, problems have been solved with revolutions. For example, the problem of communication. Someone discovered electricity, and voila, there you are, communication of today. And somebody was tinkering with semiconductors 60 years ago, and out of that came all the modern communications of today. Accidental discovery of penicillin really changed the medical environment. So that's the kind of thing you can't really predict what will come of these fundamental discoveries, but what you can predict is that practically every one of them will lead to some useful application. And those applications can help solve the problems that the world is facing. We're actually dealing with the issue of human survival. It's as profound as that. So anyway, we hope that the Institute for Venture Science, and by the way, we just put up the website of this institute. We're now looking for funding. We plan private funding, and I think there are wealthy people out there who feel they want to give back something to society, and those are the kinds of people that we'd like to get connected with. This is a noble endeavor. We really want to do something positive for the world, and so we're excited about this.
Yeah.
I hope that answers your question.
That definitely does, and I can tell you something that we don't need to predict, we just know is true, is that without the same type of capital support that you see big companies who are looking to make a buck from their revolutionary inventions or ideas, without the same sort of capital investment that they have, it'll be really difficult for this noble endeavor to succeed, which is why so many people who understand that there are revolutions to be had are excited about the IVS. Many members of our community have been talking about that as well, and I think that we all stand behind you 100%, and anything we could do to help, we absolutely will. Definitely.
Thank you. What you could do is provide the website URL.
Oh, certainly. It'll, in fact, while we're talking right now, I imagine it'll be on the screen, so people will have a nice laugh at that. Thank you so much for coming on here this morning with us, Dr. Pollock.
It's my pleasure.
Absolutely. Dr. Gerald Pollock, everyone.